So when looking at forces that are acting inside of a material, one variable that we introduce is what we refer to as pressure, or inside of a material it's called stress. But pressure is defined as being a force per unit of area measurement. And so we calculate it by applying this limit. So we take the force, divide it by a area over which that force is being applied, then we reduce that area, we take that limit as area approaches zero, and so the resultant force acting normal to the surface area A, we get this measurement of pressure. So, and again, inside of a material, we refer to that as stress. So we want to calculate this for what's going on inside of a soil sample. So for our purposes, we have a few assumptions that we're going to make to kind of simplify our analysis. First, whatever layer of soil we're looking at, it's going to have its own uniform properties. It's not going to vary within a particular layer. We might have two different layers of different types of soils, as we'll see in one of our examples, but within the individual layer, the properties are uniform. Second, if we're going to be talking about a saturated soil, then the water table is going to go all the way to ground level. We're going to have full saturation so that we don't have some sort of more complicated circumstance where there's water in part of the soil but not in the other. It's going to be a full saturation to make our life a little bit easier. And for now, we're just looking at the stress that the soil is experiencing due to the soil itself. So we're not putting anything on top of the soil yet. We're just studying the stress, calculating the stress that the soil experiences just because of its own weight, essentially. So under these conditions, there's only two vertical forces that are acting on a block of this soil. There's the weight of the soil itself, which is going to be affected by gravity, and then there's the reaction force due to Newton's third law, so the normal force reacting to it. So in terms of the weight of the soil, we've got the weight of the saturated soil. Again, we're going to assume we've got full saturation. So that's going to be our saturated density, so we saw previously how to calculate that, times the volume of the block of soil that we're considering. So density is going to be a force per unit of volume, times the volume of the soil is going to give us the weight of that saturated soil. And so then when we want to change that to stress, when we want to figure out, all right, what is the stress that the soil is experiencing, remember that that's a force per unit of area calculation. So we're going to take the limit, as we have it described up above, as the area is reduced to zero, of the force, so the weight of the soil, divided by the area over which that force is being applied. So that's going to be this flat surface if we imagine it for a block of soil. So if we now, instead of using the general statement that we had from up above, but getting specific to the block of soil that we're considering here, so we've got our saturated density times the volume, so Z being the height, and then L and T being the length and thickness, if you will, of the soil. So we have the saturated density times the three dimensions there, and then divided by the cross-sectional area over which this force is being applied. So the force is perpendicular to this flat surface here, so that's why A is now L times T. Well, you can see that before we apply this limit of that area, L times T approaching zero, we can do a little cross-canceling here. And so then we're left with the stress that the soil experiences just because of its own weight is equal to the density, saturated density of the soil times the thickness of the soil sample. So again, this is the stress that is just due to the soil itself. There's no structure or anything. It's just the soil and the weight of the water that is creating this stress that the soil is experiencing on its own. Now, as it turns out, experiments have shown that the water pressure, the water weight that's in those pores, does not contribute to the compaction of the soil. So therefore, its contribution to the stress doesn't really happen. And so as a result, we can calculate the effective stress. So we've got this sigma prime, where we will take the saturated density, subtract the density of the water, and then multiply that times the depth of the soil, the thickness of the soil sample, to achieve the effective stress of that material. So saturated density minus the density of the water times the depth, that's going to give us the effective stress that the soil is experiencing. So this is referred to as the effective stress principle, the idea that the water does not contribute to the compaction of the soil, so therefore we can remove that from our calculation of the stress that the soil is experiencing just because of its own weight. So the effective stress is what determines the soil consolidation, or whether it starts to fail, to slip, or to yield. So here we have an example of where we're going to calculate the effective stress that a soil is experiencing to different depths within two different layers of a soil sample. So we start off, just to make sure we understand the diagram here. So we've got this layer A, so that's going to be in the purple here. So layer A goes to a depth of 2.5 feet, and then below that, we'll put this in blue, is this layer B, which is below that layer A. And so each of these two layers have different properties. So layer A has a density of 78.6 pound-force per cubic feet. Again, that's a saturated density. And then layer B has this density of 91.2 pound-force per cubic foot. And so what we want to do is we want to figure out what is the effective stress at two different depths. So in A here, part A, we're just going 2 feet down into the surface. That means we're entirely within layer A. And then in the second example, we want to go 3 feet deep, which now means we're going to be all the way through layer A and partially into layer B. So we want to see how we can calculate the effective stress in each one of these. So let's start with part A. So remember, the effective stress is measured by taking the saturated density, and so in this case that's just going to be for layer A. We're then going to subtract the density of water, and then we're going to take all of that and multiply it times the depth of the samples. That's the formula that we defined earlier, and so in this case that's going to be a depth of 2 feet. So for our purposes here, density of layer A is going to be that 78.6 minus the density of water given to us here, 62.4, times this 2-foot depth. And so then the end result is a stress of 32.4. Now remember, those densities are force per unit of volume. If we multiply that then times a length, we're going to end up with force per unit of area. So it's going to be pound force per square foot. So those are the units on stress. That's the effective stress just 2 feet into layer A. Now we want the effective stress that goes 3 feet deep. So it's going to be all the way through layer A and then half a foot into layer B. So let's work on that here. So our effective stress is going to be a two-part calculation. So we're going to have the same thing that we did just a moment ago. So the saturated density of layer A minus the saturated density, or just the density I should say, of water times, but now we're going through the full 2.5 feet of layer A. And then we're going to add to that a similar calculation. So now that's going to be the saturated density of B minus the density of the water times the depth into layer B that we're traveling. And so since layer A is 2.5 feet, but we're going another half a foot down to get to 3 feet, so that's going to be 0.50 feet. So we're only half a foot into that layer B. So if we substitute in all of our values, saturated density of A again is 78.6. For layer B, that's 91.2. We have our density of water at 62.4. So if we take these two calculations and add them together, we ultimately end up at 54.9 pound force per square foot. So again, it's that same force per unit of area for a measurement of stress. So this is the effective stress that this particular soil is experiencing at these various depths, just due to the weight of the soil itself. This is before we have any kind of structure that's going to cause any kind of compaction to increase the force that the layers of soil are experiencing. Those are calculated separately. This is just due to the soil itself.